Hey guys, welcome to day 6. Today I thought we'd review bounded region problems. So let's just start. First off, let's start with area of a bounded region. So the most common way we see this is something like this. Oftentimes they assign, they call a letter for that region. So let's say they call this region S. So region S is bounded by f of x and g of x. Find the area of S. Well, in order to solve this problem, we need to first consider those intersections, right? Sometimes they'll label the intersections for you. They'll give you the points at the intersections. Sometimes they make you find them. When they make you find them, you usually have your calculator, right? You can just do second calc intersect. Right? And it's going to tell you an x value and a y value. So let's say this intersection is a comma f of a. This intersection out here is b f of b. To find the area of S, then we just integrate from the left x value of a to the right x value of b, of top function minus bottom function dx. So to find the area, we can do the integral from left to right of top function minus bottom function. Also, that's usually all you have to do for area. Sometimes we can also find area by integrating bottom to top of right function minus left function. In most cases, I would not suggest doing that. However, it is possible. When you do that, you have to integrate from the bottom value, the bottom y value, to the top y value. And when you do right function minus left function, if the functions are probably solved y equals something in terms of x, you need to solve for x, so it says x equals something in terms of y. Then our integral would be dy instead of dx. Again, very rarely do they force you to do that, so it's not quite as important, but we might see some examples in class where we kind of have to do that. Okay, next. We'll talk about the disk method. The disk method is when we have a region where one of the boundaries is also what we're revolving around. So here's f of x. This intersection is at the x value a. And then at b, we have a horizontal line x equals b. Okay, so the region, again, I'll call it region S. The region S is bounded by f of x, right, the curve, the y-axis, or sorry, the x-axis, and the horizontal line x equals b. So there are our boundaries. Okay, our boundaries are f of x, the x-axis, and x equals b. Okay? So the x-axis is one of our boundaries, and then you're asked to revolve S around the x-axis. So rotate S around x-axis. And then find volume. So again, when we revolve this thing around the x-axis, it's going to make something that looks kind of like a bullet. Okay? and it's going to be solid. There's no hole in the middle. Okay. If I took S and revolved it around the line y equals -1, that would be a washer method. This is simply a disk method, with this distance here being the radius of that disk. And our general form here is volume is always going to equal the integral from left to right, or pi times the integral from left to right of that radius squared dx. So in this case, my volume would be pi. I'm just finding the area of that circle, multiplying by dx to get the volume from the thickness. So this would be pi integral from a to b of my radius. This distance right here is different, right? This radius is smaller, this one's bigger. Depending on where I am, the radius is always changing, but it is always the length f of x. The distance from the function f of x to the x-axis, that distance is a distance f of x. So I have to square that because that's my radius. So it's f of x squared dx. There's no big radius and little radius here because it's a solid figure. Okay? This thing would look something like this, with lots of little circles. And we're just going to sum up all of those circles from A to B. Okay? That's the disk method. Let's talk about, that's disk method around the x-axis. Let's talk about the disk method around the y-axis. So this one I'm going to use an actual function here. So here's what I have. My function is bounded by, or my region is bounded by y equals x squared, the y-axis, and the horizontal line y equals 4. Okay, so this is my region, S, and now I'm revolving around the y-axis. Okay. So again, I want to stack up all those circles, but all those circles are stacking vertically, so I have to stack from bottom to top. I know that this right here is the point 2, 4. Okay. I know this point right here, that's the point 0, 0. So, but now my radius is this direction. This is my radius, okay? I have to do a couple of shifts here. My volume is going to be pi. The integral, instead of going left to right, 0 to 2, it has to go from bottom to top. So it has to go from 0 to 4. My radius is not x squared, because the other shift I have to make is I have to solve this function in terms of x. So x would equal root y. So my radius then, the only radius, there's only one radius here, my radius then is root y. So I have to square the radius in my function, my integrals in terms of dy instead of dx. Okay? Anytime you do things, revolve things around the y-axis or any other vertical line, we need to make those changes. We have to integrate, instead of left to right, we have to do bottom to top. And we have to solve the functions in terms of x equals, so we can do dy. All right, let's check washer method real quick. Now let's talk about rotated around a horizontal line. Again, that means x-axis or or y equals some constant. Okay, those are horizontal lines. I'm going to talk about one above. This will be an example, or sorry, I'm going to talk about one with a line below and one with a line above. Okay. Here we have f of x. Here we have g of x. This is the x value A, this is the x value B. Okay, for those intersections right here and right here. So first off, let's look at it rotated around the x-axis. If we revolve this thing around the x-axis, we notice it's going to have a hole in the middle. It's going to be hollow, right? Going to have a rotation like this and a rotation like this. The big radius will be f of x, while the little radius is g of x. The formula is always pi integral left to right of big radius squared minus little radius squared dx. The big radius here is simply the distance between the x-axis and f of x. So for this particular one, we'd have pi integral from a to b of f of x squared minus g of x squared dx. Okay. So this would be for around the x-axis. But what if we did another horizontal line that was lower than the x-axis? So we have something like this. So we have f of x and g of x. Again, this is A, this is B. And let's say we're revolving around the horizontal line, y equals -3. Okay. Now, this is going to make a much a bigger circle. Now, my big radius is still going to be tied to f of x. But as a reminder, that distance is f of x. So my big radius is not simply f of x. It's f of x plus this distance. Well, this distance is always 3 because we have the line y equals -3. So this entire big radius here is always going to be f of x plus 3. My little radius then will be this distance, which is g, and this distance, which is 3 again. So my little radius here will be g of x plus 3. So my volume will be pi integral from left to right of big radius squared minus little radius squared, whole thing, running out of room here, dx. Okay? But what about if it's a horizontal line that's above the region? Well, it's going to look a little different. So here's my f of x, here's my g of x. This I'm just calling A, this I'm just calling B. But now, let's say I'm revolving this thing about the horizontal line y equals 5. So let's say that horizontal line y equals 5 is now above my region. Well, again, when I revolve this thing upwards and around, it's going to make a big radius that actually ties to G and a little radius that actually ties to F. So I always like to think to myself, okay, what's going to be my big radius? Well, that distance is my big radius. Okay, but that's not G. This distance right here, that distance is G. this whole distance is 5. So the big radius, the one that I'm actually looking for right here, is 5 take away g. So whenever we revolve above, it's always whatever that constant is minus the function, the lower function, to get our big radius. So my big radius here would be 5 minus g of x, where my little radius, again, this distance is still 5. This distance is now f. This length is 5 minus f. So little r would be 5 minus f of x. Therefore, my volume would be pi integral left to right, a to b, of 5 minus g of x squared minus 5 minus f of x squared dx. Okay. So we might have to do washers below, washers above. Either way, we can do it. When it's below, we always take the top function and add however far below it went. When it's above, we take the number and subtract the bottom function to get the big radius, subtract the top function to get the little radius. Okay. If we're doing a washer method around a vertical axis, okay, let's say I have y equals x squared, and I have the line y equals 2x. So again, I'd have the point 0, 0, and I'd have the point 2, 4. Let's say I'm now revolving this around the y-axis. Well, now I'm stacking these washers from bottom to top. My big radius is going to tie to my right function. My little radius is going to tie to my left function. But remember, I always have to make two switches. My volume is going to be pi integral. Instead of doing left to right, 0 to 2, I must do bottom to top, 0 to 4. The big radius is my right function, but I have to solve this for x equals. So x is going to equal root y. I have to solve this one for x as well. X equals y over 2. So my big radius is root y squared minus my little radius, which is y over 2 squared. And again, the whole thing will be dy instead of dx. Okay. Last thing we need to know from this is region is base of solid. First, let's look perpendicular to x-axis. Okay, here's f of x. Here's g of x. Once again, this is an intersection at A here. This is an intersection at an x value of B here. So to solve these ones perpendicular to the x-axis, we just integrate left to right of the area of the shape that's being created, dx. That will give us the total volume. Okay? Now they could give us lots of shapes. They could give us squares, isosceles right triangles. They could give us semicircles. Let's start with an easy one, squares. They say cross-sections perpendicular to the x-axis are squares. Okay? So there is a square with its base in the plane, and then it pops out of the screen at you, right? Now that's hard to do. I'm just going to make it, right? That square, it's not laying flat like the plane is. It's pointing straight at you, okay? So we know that this square is going to have an area of base times height. It's the same thing, right? Because all four sides of the square are congruent. The question is, how do I find this length? Well, the length of that line is always top minus bottom. Okay. So the area of this shape will be f of x minus g of x times f of x minus g of x. Or another simpler way to write it is f of x minus g of x quantity squared. So my volume here would be integral left to right of f of x minus g of x squared dx. Okay. Let's try on with a different shape. We got A here, B here. Let's do the tough one. Let's say the perpendicular to x, the cross sections are semicircles. So again, the base of the semicircle, the diameter is in the plane, and it pops out at us like that. So again, my volume is just going to be the integral from left to right of the area of this shape, okay? This shape is a semicircle. What we know is that this distance right here, which corresponds to this distance right here, that's the length f of x minus g of x. Well, the area of the semicircle is half of the area of the circle, half pi r squared. Problem is, notice, this requires radius. This f of x minus g of x, that is the diameter. The diameter is f of x minus g of x. So the radius would be half of that. F of x minus g of x over 2. Half pi can go out front. Then I just have to do radius squared. The radius squared is f of x minus g of x. That's the diameter, divided by 2 makes it the radius. Squaring it and adding dx gives me that volume. Okay. When we have perpendicular to the y-axis, we just have to integrate from bottom to top. When we do right minus left, and once again, we have to solve if they're in terms of y equals, we have to get them in terms of x equals. Okay, that was a lot for today, but good. Hopefully it came back to you since we haven't done this one that long ago. Talk to you guys later. 2 chains. Bye.